Hello everyone, this is Professor He. Nice to see you again. The topic of this task is an overview of fuels and combustion. In the preceding projects, we limited our consideration to non-reacting systems, systems whose chemical composition remains unchanged during a process. This was the case even with mixing process, during which a homogeneous mixture is formed from two or more fluids without the occurrence of any chemical reactions. In this project, we specifically deal with systems whose chemical composition changes during a process, that is, systems that involve chemical reactions. We focus on a particular type of chemical reaction known as combustion because of its importance in engineering. We should keep in mind, however, that the principles developed are equally applicable to other chemical reactions. Any material that can be burned to release thermal energy is called a fuel. Most familiar fuels consist primarily of hydrogen and carbon. They are called hydrocarbon fuels and are denoted by the general formula of CnHn. Hydrocarbon fuels exist in all phases, some examples being coal, gasoline, and natural gas. The main constituent of coal is carbon. Coal also contains varying amounts of oxygen, hydrogen, nitrogen, sulfur, moisture, and ash. It is difficult to give an exact mass analysis for coal since its composition varies considerably from one geographical area to the next, and even within the same geographical location. Most liquid hydrocarbon fuels are a mixture of numerous hydrocarbons and are obtained from crude oil by distillation. The most versatile hydrocarbons vaporize first, forming what we know as gasoline. The less volatile fuels obtained during distillation are kerosene, diesel fuel, and fuel oil. The composition of a particular fuel depends on the source of the crude oil as well as on the refinery. A comparison of some alternative fuels for transportation to gasoline is given in the table. Note that the energy content of alternative fuels per unit volume are lower than that of gasoline or diesel fuel, and thus the driving range of a vehicle on a full tank is lower when it is running on an alternative fuel. The oxidizer most often used in combustion process is air. For obvious reasons, it's free and readily available. Pure oxygen, O2, is used and an oxidizer only in some specialized applications such as cutting and welding, where air cannot be used. Therefore, a few words about the composition of air are in order. On a mole or a volume basis, dry air is composed of 20.9% oxygen, 78.1% nitrogen, 0.9% argon, and small amounts of carbon dioxide, helium, neon, and hydrogen. In the analysis of combustion process, the argon in the air is treated as nitrogen, and the gases that exist in trace amounts are disregarded. Then dry air can be approximated as 21% oxygen and 79% nitrogen by mole numbers. Therefore, each mole of oxygen entering a combustion chamber is accompanied by 3.76 mole of nitrogen, a chemical reaction during which a fuel is oxidized and a large quantity of energy is released is called combustion. During combustion, nitrogen behaves as an inert gas and does not react with other elements, other than forming a very small amount of nitric oxides. However, even then, the presence of nitrogen greatly affects the outcome of a combustion process, since nitrogen usually enters a combustion chamber in large quantities and low temperatures and exits at considerably high temperatures, absorbing a large proportion of the chemical energy released during combustion. We should also mention that bringing a fuel into intimate contact with oxygen is not sufficient to start a combustion process. The fuel must be brought above its ignition temperature to start the combustion. The minimum ignition temperatures of various substances in atmospheric air are approximately 260 degrees centigrade for gasoline, 400 degrees centigrade for carbon, 580 degrees centigrade for hydrogen, 610 degrees centigrade for carbon monoxide, and 630 degrees centigrade for methane. Proportions of the fuel and air must be in the proper range for combustion to begin. For example, natural gas does not burn in air in concentrations less than 5% or greater than about 15%. During a combustion process, the components that exist before the reaction are called reactants, and the components that exist after the reaction are called products. Consider, for example, the combustion of 1 kilomole of carbon with 1 kilomole of pure oxygen, forming carbon dioxide. Chemical equations are balanced on the basis of the conservation of mass principle, which can be stated as follows. The total mass of each element is conserved during a chemical reaction. The total number of moles is not conserved during a chemical reaction. A frequently used quantity in the analysis of combustion process to quantify the amounts of fuel and air is the air-fuel ratio, AF. It is usually expressed on a mass basis and is defined as the ratio of the mass of air to the mass of fuel for a combustion process. The air-fuel ratio can also be expressed on a mole basis as the ratio of the mole numbers of air to the mole numbers of fuel. But we will use the former definition. The reciprocal of the air-fuel ratio is called the fuel-air ratio. Okay, that's all for this task. Thank you very much and see you next time.